Welcome back to our third and final segment. We're still talking electric field at a point, but now we just want to focus our attention on net electric field at a point. But before we do that, let's quickly look at the mathematical relationship between electric field at a point and the magnitude of charge. So we are saying that E is directly proportional to the magnitude of the charge, okay, provided we keep the distance from the surface of the charge that creates the field constant. So once we do that, we know that when we increase the amount of charge, we use a charge that's bigger, so the value of E will also increase. So electric field at a point is directly proportional to the magnitude of the charge that creates the field. But remember, direct proportion, it means if we increase the charge, the value of E will also increase in the same proportion. So what that simply means, from our sketch of the graph, we've got E versus Q, right? Okay, this is just a sketch just to show the relationship, okay? So we change in Q, okay? Q is in coulombs, right? And then on the vertical axis, we've got E, which is electric field at a point in newtons per coulomb, right? So this is the relationship that exists between those two, right? Let's shift our gears a little bit and look at net electric field. Now, determine net electric field at a point due to two charges. So we're talking about an E net in this case, okay? Right? So E net is a combination of, two charges. We've got a common point which is in the field of both charges, and then we want to know what is the effect on the unit positive charge at that point due to the two charges. So the 2 point charges are 6 centimeters apart. That's the distance between the 2 point charges, okay? And B is the midpoint, okay? Midpoint, it means B is equidistant from Q1 and Q2, right? Then calculate E net of the field at point B. So the E at B is due to, let's call this one Q1. Let's call the 3 microcoulombs Q1, and then let's call the negative, let's label the negative 1 microcoulombs Q2, right? So this is the scenario that we have. Right, let's do the science. Now, at point B, we place a unit positive charge, okay? There are two charges exerting a force on the unit positive charge placed at point B, right? So at point B is a point. Let's get that clear. So at point B, let's put a unit positive charge there. That's a free vector diagram that we want to come up with, okay? So I've used a dot. It will be a free in the form of a free body diagram. So the unit positive charge that is placed at point B is positive. Now Q1 is also positive. So the force exerted by Q1 on the unit positive charge placed at B is in that direction, right? So we'll call that E due to Q1, right? So that's the direction of the E at point B due to Q1. Why is it in that direction? We've demonstrated that using the simulator, okay? What about the force experienced by the unit positive charge at the same point B due to Q2? Now, Q2 is negative, so it will exert an attractive force on what? On the unit positive charge. Then we've got our E due to Q2, right? So this is our vector diagram. Now, this vector diagram will be very important in terms of the direction, okay? So E net, in this case, becomes equals to E due to Q1 plus E due to Q2, right? So we'll say, because both of them, these vectors are to the right or towards Q2, so we'll take that direction as positive, okay? We're choosing our direction. The direction towards Q2 is positive, okay? So if we do our calculation of E net, we'll have our E net is equals to K Q1, okay, over R squared plus, the plus in this case is for the net, plus K Q2 over R squared, right? So we're still using the formula that we're very familiar with, okay? Now, if we carry out our substitution for E net, we'll have something of this sort. E net is equals to 9 times 10 exponent 9, okay? Wait a minute. The magnitude of Q1 is given in microcoulombs. So we need to carry out the necessary conversions before we substitute into the equation. So if we convert microcoulombs to coulombs, it will be 3 times 10 exponent negative 6, right? The square of the distance is 3 centimeters. So we need to convert 3 centimeters to meters, which is 3 times 10 exponent negative 2. We square that distance. So this substitution is for E due to Q1. What about E due to Q2? So this is plus E due to Q2. So we do our substitution, 9 times 10 exponent 9, right? Multiplied by our value for the charge Q2. Now we will ignore the negative because it will mess up our direction, because we've used the vector diagram to determine E due to Q2, which is saying to the right. So if we put a negative there for the magnitude of the charge, it's going to mess up our direction. So that's the main thing in as far as determining E net. So this is 1 times 10 exponent negative 6 over the square of the distance, which is the same 3 times 10 negative 2, and then we square that distance. Now, what remains after that is basically the maths, okay? So we can go to our calculator very quickly and then try and get that value quickly, because we've managed to do our substitution, okay? So actually, all the science has been done here. What remains is for us to determine the value of E net, right? So this is the scenario that we have. Let's calculate the first E due to what? Q1, which is 9 times 10 exponent 9, okay? Multiplied by 3 times 10 exponent negative 6, okay? Right? Divided by 3 exponent negative 2. Maybe we need to square that, right? Let's put it in open bracket, okay? 3 times 10 exponent negative 2, okay? And then we square that. So what you see there in terms of what we have punched into the calculator, it would give us the value of E due to Q1. Okay, but we know that it's the sum because they're in the same direction. We put another fraction, okay? 9 exponent 9 multiplied by 1 times 10 exponent negative 6, okay? And then we square the distance, same distance, because we're told that they are equidistant, which is 3 times 10 exponent negative 2. Okay, we close that and we square the distance. So if we punch the equal to, it will give us the value of E net. So if you count there, 1, 2, 3, 4, 5, 6, so it's 40 million newtons per coulomb to the right. So this is 1, 2, 3, 4, 5, 6, 7. Okay, there are 7 zeros. So our E net, right, just to go back to that, okay, our E net is equals to 40 million, which is 4 times 10 exponent 7 Newton per coulomb. This is the magnitude, but the direction is towards Q2 or to the right, okay? Or to the right. So this is how we determine the magnitude of E due to 2-point charges at a common point, right? So there's a lot of things. Just to go over it, we need to use the vector diagram because we've emphasized the vector nature of E due to a point, at a point due to more than one charge, okay? And then here's the vector diagram that I was talking about. So we managed to come up with that. E due to Q1, okay, that's the signs, and then E due to Q2. They're in the same direction. Okay, let's change gears and look at something different. The net electric field at a point, okay? 2-point charges, we've got Q1 and Q2, right? Which are 30 centimeters apart, okay? And then P is a point that is 10 centimeters east of charge Q2. Direction, direction, and direction. So the moment we see that, we can no longer use left and right because it's prescribed for us that we'll take, because these are collinear. Q1, Q2, and point P are collinear, it means they fall on a straight line, okay? So towards P is east, towards Q1 is the opposite, which is west. So if we can say, for argument's sake, from the onset, okay, naturally I would choose, because I'm right-handed, I'll choose east as positive, but it doesn't have to be like that. So we will take this one as positive, or as an example, okay? Now use a vector diagram to determine the electric field at point X, but we are talking about the net electric field at point X. So what are we looking for here? We're looking for E net. How is this scenario different from the previous one? The three are collinear, the two charges and the point. Now, first we've got the two charges, and then point P is to the right of the two charges. That's the main difference, okay? So if we were to do our vector diagram, okay? So here is our point P, okay? There is our point P. I'll just do it just next to point P just to illustrate the vectors, okay? Now, Q1 is positive, right? Q1 is positive, while Q2 is negative. So E due to Q1 at point P. So if we place a unit positive charge here at point P, due to Q1, it will experience a force to the east, because those are like charges. So this is our E due to Q1, right? That's our vector, first part of the vector diagram, okay? And then E due to Q2. Q2 is negative, while the unit positive charge is positive, as the name suggests. So in which direction will it experience a force? It will experience a force westwards. So this is E due to Q2. But I also need to just highlight something. These are just sketches. This is not a scale diagram. When we draw the vector diagram, we're not necessarily indicating that this is the actual magnitude. For us, it's just to get a sense of the direction. So this is not a scale drawing. So whether the tail is longer or shorter, the emphasis is on direction. Remember, it's the vector nature of the quantity electric field at a point, right? So this is our vector diagram. So if we were to determine E net, then the mathematics follows. E net is equals to E due to what? Q1, okay, plus E due to Q2, right? So the plus suggests something about the addition, the resultant, the sum, which is the net, right? And then E due to Q1, now we know the formula. We can go straight and say 9 times 10 exponent 9, okay? That's the K, multiplied by 3 times 10 exponent negative 6, that's the microcoulomb, divided by 30 times 10 exponent negative 2, okay? We square that distance, right? Plus, okay, but the plus here, it's for the sum. But then E due to Q2 is westwards, which is negative for the direction, okay? 9 times 10 exponent 9 multiplied by 5. Remember, we ignore the negative, because if we say minus, minus is going to be plus, and it would be as if E due to Q2 is also eastwards. So we would ignore the negative sign of the charge and consider the direction, because it's a vector, right? 5 times 10 exponent negative 6, okay, divided by the distance. How far is point P from charge Q2? It's 10 centimeters. So it's going to be 10 multiplied by 10 exponent negative 2. We square that distance. So this is what we're going to get for our E net, right? So our E net, in this case, becomes, then we can go to our calculator, right? So from our calculator, we are immediately able to say, okay, there are two sides to it. It's going to be 9, or we put that fraction because that's what it is, a ratio. 9 times 10 exponent 9, which is the K, multiplied by 3 times 10 negative 6, which is actually the magnitude of charge of Q1, okay? Divided by, let's put that into brackets because our intention is to square the distance. So that's going to be 30 multiplied by 10 exponent negative 2, okay? We'll square that as well, okay? Minus is for to say E due to Q2 is in the opposite direction of E due to Q1. Remember, net takes into account the direction because these essentially are vectors, right? So 9 exponent 9, that's the K value, multiplied by the 5 times 10 exponent negative 6, okay? We divide that by the distance, which is 10 multiplied by 10 exponent negative 2, okay? Which is, we're changing those centimeters or converging from centimeters to meters. Do not forget to square the distance, okay? So this gives us the value of our E due to those 2-point charges at point P. So this is like negative. And negative says it's actually west in terms of direction, okay? Because we said that if towards P is east, which is positive, then if the answer is negative, our interpretation of it is that it's going to be westwards. So how many zeros do we have here? 1, 2, 3, 4, 5, 6, okay? So it's 4.2, okay? Okay, it's actually negative 4.2, which is 4.2, okay, times 10 exponent 6 Newton per coulomb. Then that negative suggests that the direction of net is west. So that's the magnitude, that's the direction. All right, now in closing, in summary, we understand that electric field at a point E is the force experienced per unit positive charge. That's straightforward, okay? It's a vector, we know that, and the field is directly proportional to the magnitude of the charge. So these are some of the legal detail that we need to remember, but the science around problem solving needs to be consistent. Electric field at a point, net electric field at a point are both vectors. So there's an emphasis on direction, direction, and direction. Having said that, let's try and say, okay, if a question is given, you need to do the science first. The science is dealing with the vectors. Because of time constraints, we've reached the end of our session for today. Hopefully you take something out of these discussions. For myself, it's goodbye for now.